Okay, so in this lecture, we will cover what's known as the E1 reaction mechanism. So if we take this reaction, take tert butyl chloride and react it with water versus water, if you remember that symbol means heat, then you get two different products. So the major product here with just water would be the alcohol, but if you heat this reaction instead, you do get some alcohol, but the major product would be the alkene. And in both cases, you get HCl side product. Okay, so what is the difference? So why, well, let's look at the mechanism. How is the alkene formed in this reaction? Okay, so this leading to the alcohol, this is what's known as an SN1 reaction, and leading to the alkene, this is following what's known as an E1 mechanism. So the E1 mechanism is similar to the SN1. So the first thing that happens is the leaving group leaves, takes the 2 electrons in the carbon-chlorine bond with it. So now that carbon is electron deficient, so you make a carbocation, and you have a Cl- leaving group. And then if this was going to do an SN1, then what would happen is the nucleophile would attack, right? And you would get this intermediate, which then you lose a hydrogen. And you would get HCl side product, right? Or you could show Cl- taking the hydrogen off. So that's if it did an SN1. But what this can do instead, so let me just draw the carbocation again. And let me sketch one of the hydrogens out. So what can happen instead? So here H2O can act as a base. In this case, H2O is acting as a nucleophile, but water can act as a base. And so what it can do is you can take a lone pair of electrons on water, and it can take a hydrogen atom off. And those 2 electrons in the CH bond can become a carbon-carbon double bond. So if you notice, the arrow starts on the bond and the arrow ends up on the other bond. That means you're taking those 2 electrons and making another bond with them. So now you get the alkene. And then you would have H3O plus. And then Cl- can take a hydrogen. Right, so you get your H2O still, and HCl side product. So that's the basic mechanism for an E1 reaction. So what does E1 stand for? The E stands for elimination. So what did you eliminate in this case? You eliminated HCl. So you lost a hydrogen from here, and you lost the chlorine, so you lost an HCl molecule. Right? And the 1 stands for it's unimolecular. Right, so in the E1 mechanism, this first step is the rate determining step, just like in the SN1. So the only thing involved in the rate determining step is the alkyl chloride. The water has not come into play yet. So the rate of the reaction does not depend on the water, it only depends on the alkyl halide. So one characteristic of an E1, just like the SN1, is that the rate only depends on the concentration of the alkyl halide. not the water. So if we took this reaction and we doubled the concentration of water, no effect on the rate. Double the concentration of the alkyl chloride, the tert-butyl chloride, the rate would double. Triple it, the rate would triple. Okay, so E1 reactions, then you always make alkenes. And these reactions are always in competition with each other. So even without the heat, so your major product would be the alcohol, but you would get some minor product. You would get some E1 elimination because they're always in competition with each other. And if you heated this, so without the heat, then this is major, and the alkene is minor. With the heat, then this is major, and you would still get some alcohol, but it would be the minor product. Okay, so what's the difference? So why does the heat tend to favor things? Why does heat tend to favor the alkene? Well, so in the SN1 reaction, you have two molecules, right, that become two molecules. Whereas when you do the E1 reaction, one molecule becomes two molecules, right? Because the water basically ends up unchanged. So it participates in the reaction in subsequent steps, but overall, you get the water back, so the water ends up unchanged, right? As this mechanism showed. So one molecule becomes two molecules. If you remember from General Chemistry 2, this concept of entropy. Entropy is a measure of order and disorder, right? So if you go from two molecules in the SN1 to two molecules, not a big change in entropy. But if you go from one molecule in the E1 to two molecules, the alkene plus HCl, that goes to more disorder, and the heat tends to favor more disorder. So as you heat the reaction up, the reaction tends to favor more disorder, and so the E1 reaction becomes predominant. Okay, so heat favors. So heat favors E1 over SN1. So similar to SN1 weak nucleophile, the E1 is favored by a weak base, and whatever is a weak nucleophile is generally a weak base as well. So we'll be looking at the same bases. So water, alcohols, right, would typically be the bases that we look at for E1. You do make a carbocation. So what do you have to know about carbocations? You have to remember that every single time you make a carbocation, you have to watch out for rearrangement. And we'll work some examples to try to illustrate that. So let's take this example as an illustration. So again, if we, so this is a secondary, so SN2, SN1, and E1 are all okay. And in terms of the nucleophile base, this is weak. So that's going to eliminate SN2, and heat is going to eliminate SN1. So the only thing left is E2, so this is going to do an E2 reaction. So if we step through the mechanism, first thing that happens is the chlorine leaves. And you would make that carbocation. And will that carbocation rearrange? Yes, it will. If you go to the adjacent positions, there's a hydrogen here that you can move to there. Which would give a tertiary carbocation. And so that's more stable. So you go from secondary to tertiary carbocation. And so now this is going to do an elimination. So this will act as a base. So it's going to take one hydrogen away from a carbon that's adjacent to the carbocation. So in this molecule, then, there's 3 possible places where you could take a hydrogen from. You could take a hydrogen from that carbon, or from that carbon. So basically then you could make a double bond there. And if you make the double bond there, then there's a cis and trans possibility. So that's cis that's illustrated. And that will be the trans isomer. Or you could put the double bond, so let's call this taking the hydrogen from A, or taking the hydrogen from B, whoops. You could put the double bond there, and if you put the double bond there, there's cis and trans possibilities. The one that is drawn is trans. Or you could have put the double bond like, oops. So if the methyl was there and hydrogen was here, then that would be the cis isomer. Or you could have took the hydrogen from C and you could have made that, right? Okay, so from this alkyl halide, after rearrangement, then now there's 5 different alkenes that you could have made in an E1 mechanism. So which one of them is going to be the major product? Well, now you go back to what we learned in earlier lectures. Let's classify them. So this will be tetra, and this will be tetra substituted. This would be tri substituted, and this will be tri substituted, and this will be di substituted. So tetra substituted is more stable than tri, and tetra substituted cis, so cis is more stable than trans, so this would be the major organic product. Okay, so this is another characteristic of an E1. Is where the product is the most substituted alkene. Is the major product. So the most substituted alkene, let's get this out of the way. So the most substituted alkene product is called the Zaitsev product, or also called, well, just spelled different. The Zaitsev product. And the least substituted alkene is called the Hoffman product. But that's not important. So that's not what's going to be made here, but as we'll see when we talk about E2 reactions, then depending on the conditions, you could have the major product as being the Zaitsev product, or the major product could be the Hoffman product, depending on the conditions, but that's not true for the E1. For the E1, you just always make the most substituted alkene, the Zaitsev product, as the major product. So the Hoffman product would be this one. Because it's the least substituted, and then these two are both tetra substituted, so they would be Zaitsev products, but the trans is more stable than cis, so that would be the major product for this reaction. Okay, so rate, heat favors, weak base. Make a carbocation, so look out for rearrangement. You make the most substituted alkene, that's the major product. And I don't recall if there should be a 6th characteristic or if that's basically what you need to know for an E1 elimination reaction. So if we just take one more example, so if we take this molecule with water and heat, convince yourself, first of all, or check that it fits the characteristics for an E1. So if we classify this is secondary, so that's okay for SN2, E1, SN1. This is weak. That's okay for SN1, E1, but not for SN2. And this is heat. So that's okay for E1, but not okay for SN1. So the major product should be the E1 product. So now you just have to know how to sketch what that's going to look like. So if we work the mechanism again, bromine leaves, takes the 2 electrons with it. So that would be your carbocation. And then whenever you make a carbocation, look to see if it can rearrange. So look at the carbons adjacent to it. Is there a hydrogen or a methyl group that you can move to make it more stable? And there is, in this case, there's a hydrogen there. So we can do a 1,2 hydride shift. So the hydrogen with its 2 electrons migrates to the next carbon. And now the positive charge is there. And now you're going to do the elimination reaction. So water is going to act as a base, and it's going to take off a hydrogen. So first of all, let's decide how many places can you put the double bond. So you could put the double bond here, right? Because you're going to lose a hydrogen from here, or from here, or from here, because the hydrogen has to come off the position next to the carbocation. So we could put the double bond at A, or we could put the double bond at B, or we could put the double bond at C. So which one is going to lead to a more substituted alkene? So if you put it at C, so if we follow pathway C, the double bond there, that's going to give you a tri-substituted alkene, right? Because that carbon, the double bond has 3 carbons attached to it. If we follow pathway B and put the double bond here, that's going to be tetrasubstituted, right? Because that alkene has 1, 2, 3, 4 carbons attached to it. And if we follow pathway C and A instead, and put the double bond there, then that would be tri-substituted, right? Because that carbon, that one, and that one attached. So this one be the major organic product. More substituted alkenes, the major product. And if we finish that mechanism off, how do we make A? So we needed to lose, or how do we put the double bond at B? So we needed to lose the hydrogen on that carbon. So sketch it out. Water takes that hydrogen and the 2 electrons in that bond. We move down to make a double bond between those 2 carbons. And then that's the mechanism. So again, you don't have to show this part, but it's there. So you make the H3O plus, and then since we lost Br minus in this reaction, the side product, so Br minus, well, take a lone pair, make a bond to H. So you get your water molecule back, and HBr side product, but we're mainly interested in the major organic product. Okay, so that's the basics for an E1. Let me just finish off this mechanism, so show you how the major product is formed here. So let's see. So we need our base, and it needs to lose a hydrogen from carbon A. So we sketch that hydrogen out, take 2 lone pairs of electrons there, make a bond to that hydrogen, and the CH electrons become a double bond, and then that would give you the tetrasubstituted alkene. Okay, so that's it for the E1 reaction.